Hey everybody, today we're talking about Chapter 2, Section 4. We're talking about complex numbers. And you don't have to be a doctor like this guy to do complex numbers, and it's definitely not extremely complex. It's just complex because we're talking about complex numbers. Now remember, from way back when, we used to say, oh, you can't take the root of a negative. Well, now we decided, okay, you can take the root of a negative, and that makes it a complex or imaginary number. So that letter I represents the number for the root of -1. So I to the 1 power is just the same as the root of -1, or we can call that I. If I have I squared, that's like saying the root of -1 times the root of -1. Remember, the root times another root of something identical cancel each other out. So I can write this as the root of -1 squared, which this squared and this root cancel, so I just get -1. So I squared is really -1. Now I cubed, couldn't I write that as I squared times I, right? Well, I squared I know is just -1, and I know I can just be written as I, so that's -1 times I. So I cubed is really -I. And lastly, if I've got I to the 4th, I can write that as I squared times I squared, right? Well, I squared is that -1 from before, so we say -1 times another I squared, which is -1 again. Well, isn't -1 times -1 +1? So just keep in mind here that I equals just I squared equals -1, I cubed equals -I, and I to the 4th equals 1. So once you get past I to the 4th, I to the anything else can be written as I to the 4th with a remainder of your exponent. So in this case, it's I to the 4th times I squared. Well, isn't I to the 4th just 1? So basically, after this, anything else, you just keep pulling out those multiples of 4 and the exponent, which is just I to the 4th, which is 1. And then you end up back in I squared, which is really just -1 here. So when you start to see I to the sum exponent, you just know we can pull out multiples of I to the 4th and make it equivalent to these simplified combinations of our complex numbers. Okay, so let's talk about what complex numbers really are. A complex number has 2 components. It has a real part and an imaginary part. And we usually write it as A, or the real part, as it goes right here. And the imaginary part is here. So again, A is the real number because by itself it just looked like a regular number, and BI is the imaginary part because it's got the I on it. And together, it's what we call a complex number because it has both. And there's this property that says the equality of complex numbers is that if A plus BI equals, and actually I'm going to do this in a different color. If A plus BI equals C plus DI, then these match up and A equals C, and if BI equals DI, then the value of B will equal D. So how do we do addition and subtraction of complex numbers? Well, if I add some complex number A plus BI plus C plus DI, I can simplify that and take our real 2 numbers, our parts of the real numbers, is A plus C plus, and then take the imaginary parts and separate them out as well. When I'm finding the difference, just keep in mind that we can still separate, but it's going to go A minus C is the real part. And then it's going to be BI minus DI. So that's why we say B minus DI here. So let's do this example. This example says the complex number 3 minus I plus the complex number 2 plus 3I? Well, because we know up here what that's going to look like, I can compare the similar parts. 3 plus 2 goes in front, plus, and then we've got negative 1I plus 3I, which is really 5 plus 2I, and that's our complex number. For the next part here, we want to make sure that when we do our separate parts, so it's 1 minus 4, and 2I minus 2I. Well, I know 2I minus 2I just gives me a 0. And then what's left here is 1 minus 4 is negative 3, and that's our answer for that. So what if you had to multiply complex numbers? So when we deal with complex numbers, we can pretty much just deal with it as if we would any other variable, except for when we multiply an I times itself, because then it changes value, just like we saw up here in our list of our values for I. Okay, which actually I'm going to go ahead and have you write them down. So remember, I equals I squared equals negative 1, I cubed equals negative I, and I to the 4th equals 1. So make sure that you've got that box somewhere on your paper. Okay, so we're looking at that, and we're going to multiply some complex numbers just like we would distribute if it was any other binomial, and this becomes 5 times negative 2 is negative 10, plus 5 times 3I is 15I. And that's our answer, because we keep the real part in front, the imaginary part in the back. Just like this one, we've got a binomial of complex numbers. So we go 2 times 4 is the first part of the FOIL. 2 times 3I is positive 6I. Negative I times 4 is just negative 4I. And the last part is negative 3I squared. Now let's keep in mind, this I squared is really, remember our list, I squared is really negative 1. So we're going to put that here. We know I squared is really a negative 1 right here. And then this can simplify. 6I minus 4I is positive 2I. And then we know negative 3 times negative 1 is just positive 3. And if we simplify that, we've got 11 plus 2I. And then the last one we're going to do, we're going to distribute 4I into both of this. So 4I times negative 1 is negative 4I, and 4I times 5I is positive 20I squared. Go ahead and simplify. Remember that I squared is really a negative 1. So this is 20 times negative 1. And we get negative 4I minus 20, which if I'm going to put that in complex form, remember it has to be a plus bi with the I at the end. So we're going to go negative 20 minus 4I. Complex conjugates. So the complex conjugate of a plus bi is a minus bi. Now notice the conjugates have some similarities and a difference. They both have the same first term, the real part of the imaginary or the complex number. They have both the same imaginary term, but where they differ is whatever's in the middle of the first complex number, the conjugate has to have the opposite sign here. So the complex conjugate of one thing will have the same terms but an opposite sign on the second one. And then watch what happens if we multiply them together. So if we multiply them, let's see what happens. A times A is A squared. And again, we're foiling. The outer term is A times negative BI is negative ABI. The inner term is positive ABI. And the last term is negative BI squared I squared. Now remember, look at this. If we combine like terms negative a plus bi and positive a plus bi, those cancel. And this I squared really becomes a negative 1. So a squared minus b times negative 1, well, that is just going to become minus b times negative 1 is really a negative b squared. And then this becomes an addition, so we get a squared plus b squared. What? Where did that I term go? It went from being there to nothing. Look, the I is gone. I'll try it again. The I is gone. Poof, it's gone. So when we multiply by the complex conjugate, the I term goes away, which is super, super helpful for what we're about to do. So what if I said, write the complex number in standard form? Standard form just means basically to simplify it. And we have this rule in math that we can't have any roots in the denominator. And remember that technically I is a root. So this I right here can't be in the denominator because it's technically a root. So we're going to do something to make that I disappear. What do you think we're going to do? How did we make the I disappear up here? Right? We multiplied by the complex conjugate. So here we go. We're going to also multiply by the complex conjugate that would make this go away. We want it to go away. So when we multiply, we're going to multiply by the complex conjugate of the denominator because we want the denominator I to go away. So if we've got 4 minus 2i is our complex number, the complex conjugate is 4 plus 2i. And when we do it to the bottom, we also do it to the top because we can't just randomly multiply a number by another number. 4 plus 2i over 4 plus 2i is just basically 1. It's the same value. It stays the same. So now I'm going to put parentheses over everything, and I'm going to FOIL. First, outer, inner. I'm going to have to erase my rule for a second here. And then last. Okay, let's leave that there for a minute. And then again, I'll do it in purple. First, outer, inner, last. And now we're going to simplify. I look here and here. Look, don't those cancel because 8i minus 8i is just 0. And then anytime I see an I squared, remember this just becomes negative 1. So on the bottom here, I've got 16. And a negative 4 times negative 1 is positive 4. So this 16 really becomes a positive 16 plus 4, which is 20. And then on top, again, I've got another I squared, which this just becomes negative 1. So 6 times negative 1 makes it a negative 6. I'm going to cancel that out. And then 4i and 12i. So here we go. 8 and minus 6 is 2. 4i plus 12i is positive 16i. And we can simplify that one more time by dividing everything by 2. And we get 1 plus 8i all over 10. And that's our answer. Now there's this other principle of a square root of a number that says if I take the root of a negative number, I can change it, and by pulling out that root and making it into an I, because remember, if I want to simplify the root of negative I can rewrite this as the root of a times negative 1, which can be simplified to the root of a times the root of negative 1. Well, that root of negative 1 is really I. So we know the root of negative a is equivalent to the root of a times I. So with that said, let's do some of these imaginary or almost imaginary numbers. We know the root of negative 3 times the root of negative 12. This can be written as the root of 3i times the root of 12i. Well, if I multiply these, This is going to give me the root of 36, and I times I is I squared. This becomes a -1, and the root of 36 is 6. So 6 times -1 is just -36. Okay. And then what about this one? We're going to go the root of -48, so we can split this up to the root of 48, I, minus the root of -27 can be written as the root of 27, I. Remember our list of perfect squares, 9, 16, 25. So all of these are perfect squares, and we're going to see what we can pull out. So 48, I can definitely pull out, actually we can pull out a 16, because the root of 16 times the root of 3 is the same as 48, which this is really 4, root 3i, minus, and if I pull out a 9 out of the 27, I'm going to get root of 9 is really 3 times the root 3i. Well, aren't these like terms? So 4 root 3i's minus 3 root 3i's leaves me 1, because 4 minus 3 is 1, and that's 1 root 3i. Almost done. How would we solve this? So if I had to solve x squared plus 4 equals 0, I would just subtract the 4 over. X squared equals -4. Take the square root of both sides plus or minus. And I'm left with x equals plus or minus. The root of -4, remember, is going to be the root of 4i, which is really plus or minus 2i. And last but not least, if we have this quadratic form, we're not going to be able to, we can factor it, I guess, but we can always use the quadratic formula. Remember that? X equals -b plus or minus square root b squared minus 4ac all over 2a. And then we're going to list off our a, b, and c, which is 3, -2, and 5. And now we're going to plug stuff into this. X equals -b, which is -2, plus or minus b squared minus 4 times a times c all over 2 times a. And we just simplify. Negative times negative is a positive 2. -2 squared is positive 4. Minus 4 times 3 is 12 times 5 is 60. And we get 6 there. And then we're going to simplify 2 plus or minus the root of -56 over 6. Now remember, the root of -56, I think we can pull out a 4 out of 56. Yep. So 2 plus or minus the root of -56 can be written as the root of 56i. And then the root of 56 can be written as the root of 4 times the root of 14i all over 6. This root of 4 is really a 2. So we get 2 plus or minus 2 root 14i over 6. And now we're going to simplify 2 over 6 and 2 root 14i over 6. So 2 over 6 can be reduced to 1. Whoops. 1/3 plus or minus 2 6 again can be 1/3 root 14i. The other way we could have written this is 1 plus or minus root 14i over 3. So either one of these is fine. All right, I'll see you in class. Have a good day.